Hello, this is example 5 in our functions and graph topic. We've been looking at inverse functions up until now. We're going to have a look at something called the modulus function. We'll come across the word modulus in vector and in matrix mathematics, but in function terms, we have to think about the idea of an absolute value of something. Now, when we talk about the absolute value of some number x, we represent it as x with these parallel lines. And so the modulus of x, or the absolute value of x, is defined by if x is greater or equal to 0, it stays as it is. But if x is negative, you multiply it by -1. What that does is it takes the quantity value of the number and ignores the fact that it's a negative value. Now, it creates an interesting function. So the graph of a modulus function is obtained first of all by drawing the original function, and then any parts of the graph which go below the x-axis, therefore the y coordinates are negative. What we're going to do is we are going to reflect it in the line y equals 0, the x-axis. In other words, we're going to represent by the same distance above the x-axis as it was below the x-axis. So as an example here, if I were to introduce this function here, here's the before function. I've just drawn a kind of random function here, and you can see that some of the y values are above the x-axis and some of them are below. If I were to consider the modulus function, then it would look a bit like this. So let's have a wee study of it. We can see that this section here obviously is below the x-axis, and if we were to take the modulus of all those values, you notice that they have to be the same distance away from the x-axis but above. In other words, we're reflecting it in the x-axis. Similarly down here, we've got negative values, and we then have to flip it up the way, reflect it in the x-axis, so it goes like that. And you'll notice that the parts that were originally above the x-axis stay above the x-axis in its original form, and all the x-intercepts stay exactly as they are. Okay, so one way in which we can do that is by drawing two graphs. It's a bit like finding if drawing a graph of the derivative of a function. It's helpful to have the original function to go on and not just draw over on top of, but use it as a basis for a new graph. So we're going to sketch a few graphs here. First of all, we need to know what the original functions look like. So it says here, sketch the graph of y equals the modulus of x. So what I want to do in the first graph is to think, what does the graph of y equals x look like? Well, that's obviously a straight line. So I can represent that in that form there. So that's y equals x. What about then y equals the modulus of x? Well, looking at that graph, all of this part here is above the x-axis, so that's going to remain. But this part here is below the x-axis, so what that's going to do is reflect that up. So it looks like that. So when I actually draw my final answer, I'm not doing it on that graph, I'm going to do it down here. So this part stays the same, but the bit for x is less than 0, it's going to go up like that, and that's going to be my final answer. Second function, y equals the modulus of x squared minus 2. So if we take away the modulus for the moment, then we're looking for just a graph of y equals x squared minus 2. We know that if we were to do a graph of y equals x squared, it would be a parabola. Oh, that's a pretty rubbish one. It would be a parabola with a turning point on the origin. The minus 2 says it's going to kind of go down there. So we end up with a point that we know, like that, and we've got, because we should really stretch these up, but there's our graph of y equals x squared minus 2. So what does that tell us? It means if we look for points above the x-axis, so they're going to stay the same, but we've got a reflection required for this part here, so I'm going to be doing something like that. So when I draw my sketch here, I'm going to have to make sure that effectively these, we don't know, we could work it out. I mean, it's going to be root 2, isn't it, if we wanted to be absolutely certain about it. So we need to make sure that the graph still kind of comes down and still goes up in the same way. But crucially, instead of it going down to -2, it's going to bounce back up and back down. So there is a turning point. I still don't like. Is that about the same? Well, we'll call it the same. We know that that's the value 2, so I can indicate that on the graph because I knew that the original turning point had a y-coordinate of -2. Any information that you've got on the original graph, carry it down, and we can indicate that as y equals the modulus of x squared minus 2. Okay, and the last one here we'll do a wee sine curve, y equals sine 2, the modulus of sine 2x. Because it's sine 2x, there will be two complete curves in 2 pi, but I'll just do the one of them. Okay, so we'll just go from 0 to pi. So we'll say, here's my sine curve, and it's only to 1 pi because it's 180 degrees because it's sine 2x. So that would be my y equals sine 2x curve. And obviously it does go on both ways, but we'll just limit it to that domain there. And if I wanted to think of negative values, well, obviously this second part here is below, so I need to reflect that up. So in my modulus, I'm going to have the original first part of it, but then it's going to bounce back up, and I'm going to basically repeat that for the second part. So ideally they should look exactly the same. And again, what we could do, we can add information, useful information, like we've still got 1 here as our maximum value, we've got pi over 2, we've got pi, so try and provide as much information as you can without having to do a lot of major analysis. So that's the idea of drawing the modulus functions. I've got here on my next screen some practice ones, so if you want to pause it, then by all means have a go at that. I'm going to show you the answers on the next slide and for you to check. So if you want to pause it and work on it, and the answers are about to come up. Okay, so if you've managed to do that, your graphs should look something like that, and hopefully this little video has helped you work out how to draw the graphs of modulus functions.